Cool. We made it to the last, new. Try that again. We made it to the last new material in applied mechanics 2, looking at momentum and energy methods. Sometimes I feel like this should be first because a lot of people are have done thermodynamics already, so this feels like review, but I don't know, usually gets lumped into one thing, momentum and energy. It's like two different ways of approaching dynamics of a system. The main thing here is that when you talk about momentum, the chain, the thing that causes momentum to either change or some change in momentum is an impulse, like a force times time, some kind of Newton second. So usually you think about that as like an explosion, like big Newton second, like lots of force, little bit of time. But it can be any force through a given time for an impulse. And then energy, when we think of like kinetic energy or potential energy, or even like how hot something is, its internal energy, all of that gets changed through work done on the system. So like actual force through a distance, working to change how much energy is in our system. So we have these two, not new definitions, but two different ways that we'll play around with like solving problems in this module. Cool. Do we need to back up and stop anywhere? Now we're rolling into something new. Does anyone have wait for me, stop the bus? We have I want to review differential equations again, or or anything. This one, the nice part about using momentum and energy is it's partly solving the differential equation already. Let me show you kind of what I mean. Let's do that. So let's say I know M, there's a mass attached to a spring, and it's this is like a lot of the oscillating problems, they all turn into this mass and spring problem. Even our pendulum, like our rotating pendulum, at the end of the day was really just a mass and spring. At least the linear version was a mass and a spring, where the spring was a length and gravity, or G over L was like K over M kind of term. So that's why I'm using this example. So with my free body diagram, I have a Kx this way, and that way, W that way is all equal to MA, like this. So negative Kx equals M times dV dt. Bless. And have you seen what's the potential energy for a spring? Do you know what that is? How much potential energy does a spring store? Not the spring store, like a spring as you stretch it, compress it. Yeah. K. 1/2 kx squared, right? Just to make your life harder, I'm gonna say V is potential energy. That's just, for some reason in physics, we always say V is potential energy. I think thermodynamics is PE, right? PE is potential energy. And what do you, sometimes U is another, no, U is almost always internal energy. Internal is not potential. But anyway, just V is our potential energy. but we can say that that's kx squared. And what is kinetic energy for just a block? Ke? No, I'm going to make up my own because I want to make your life as hard as possible. So I'm going to choose the letter for it. Not to actually make your life hard, but to try to match it with the textbook so we have like some slice of consistency in the class. But what is kinetic energy? How much kinetic energy does a moving block have? 1/2 mv squared. And in this case, it's only moving left and right, so v is just x dot. So if I have x dot, that is my x dot squared, like that. All right, now let's do a little bit of magic. I'm going to leave left-hand side the same, negative kx, but the right-hand side I'm going to say is actually m times dx dt times dv dx. You've seen this before? Not impressed? Yeah, you've already seen the sleeves pulled up. So we get negative kx is equal to mv dv dx, or negative kx dx equals mv dv. So if I integrate both sides, I end up with 1/2 k x squared equals 1/2 mv squared. I mean, I'm dropping, there's other like constants in here, like plus a constant somehow. But whenever we're using energy methods, we're taking an integral over space. Like we integrated all the force over a given distance and all the energy over a given distance. So work energy is always position velocity. Like it always gives you an answer in terms of how fast you're moving at a given spot. And then if you integrate the impulse momentum, it's always some kind of like time and changes in velocity. So time and velocity. Usually momentum methods are good for like big force, small amount of time, because there's no other way to describe it. There's like, otherwise you end up with like an infinite force for a really small amount of time. So infinite acceleration for a really small amount of time. It's hard to think about. But yeah, so we are using differential equations. It's just because we are using energy and momentum methods, they're like pre-integrated for us. Like it's already a step towards our answer. Cool. Do our first problem. All right, we're in deep space. And there's a spaceship with 10,000 kilograms of mass. Its thruster is producing 100 newtons of force in the opposite direction, anti-aligned with our spaceship's vector. How long will we need to fire the thruster to bring the spaceship to rest within absolute space? What do we know? What are some things that we know about this problem? Other than it's space, and there's like lasers and cats and aliens. Constant velocity? It was constant, but now we're applying thrust. So what happens when we do thrust? Something, yeah, so it could be a constant deceleration. Could be. So there's something changing. So we could say like our initial velocity, 50 meters per second, right? We could start with that. What's our final velocity? 0. So we want to say that that VF is 0. And I'm sure you've seen problems like this before, so I want to let you try to solve it, or solve it however you want, like whatever process you want, and I'll show like what we can do with like new impulse energy kind of methods, like what kind of questions we could answer. So we'll start there. Yeah.
On like the homework and like the project and quiz.
Yeah.
Do you care how we solve it as long as we get the right answer?
It's all the same. If you use energy method, impulse momentum, Newton's methods, Lagrange equations, if you want to look that up and teach yourself like how to use those differential equations, it's always the same answer. Like you're always going to get there.
Do you care the method we use though?
I would never say one method is more right than another. So I guess the one thing that would be kind of weird would be like use impulse and momentum to do something, and then you immediately show like, okay, here's a conservation of energy, which is impulse momentum. Like that would be a weird thing, but which I might say like, oh, why did you like? Yes, they are the same, but why are you doing it this way? Usually there's a method to my madness. Sometimes it's just straight up madness, but usually I ask you to do things as like part of the journey of learning the process. I'm all about alternative variations. Yeah. 500,000 newtons. That's how much thrust? We already know how much thrust though. In 1 second. Oh yeah, if we want 1 second stopping. But we only have 100 newtons. But yeah, if we did have infinite thrust, we could come to a screeching stop in space. Yeah, I'm not trying to catch you or anything. Genuinely interested in the process. Yeah, my acceleration is very close. So they're getting to the same thing. No, this is could be this. Oh, okay. Yeah. So like, yeah. Yeah, you can have like a thruster. I mean, or you could think of it like usually what happens is connecting asteroids. Alright. But usually what happens is like you're moving in milliseconds. You only have one thruster, so I don't do a 180 and that's the thruster. You think in the direction where you're going. Now you can try and go this way, or at least stop. So I think a lot of like spaceship tools, they assume that you can turn around. You can turn the spaceship almost instantly. You can do it a lot faster than getting yourself to stop. So it depends on how you're considering your
correct.
your arrangement. So like if you're saying your moving is positive, so you're moving to the right, all of your acceleration is negative. You want to keep thrusting towards where you're going. I only went to half the class, not for any specific reason, but I went to half, saw some of the same kind of approach. 1.3 hours. 1.38. Something, yeah. Okay. So we can say, like, it's all kind of one-dimensional, so I can use, like, left and right. My thruster is pushing me to the left of, like, negative stuff. And then my acceleration is all to the right, at least if I'm positive acceleration. So it's all negative. So A is negative, or I guess negative 100 newtons, all divided by 10,000 kilograms. That was the approach that I saw most people doing, and then you end up with, like, you can use kinematic equations or anything like that. So remember, like, impulse momentum, work energy is already integrated for you. So I want to show an approach with impulse momentum. Like same exact, it'll be the same exact answer. It's not going to change anything. And if you like vectors and doing things with three body diagrams and kinematic equations, you could do that forever. Like, you don't have to change your whole mindscape. But this can be a really useful way of reframing the problem. So instead, I'm going to draw what's called impulse momentum diagram. In step one, so before any force is applied, my momentum looks like this. M times V0. I'm moving to the right. I'm going to add to that this force of thrust times whatever that delta T is, but whatever that force of thrust times time is, that's the amount of impulse that I'm adding to this system. And all that has to be equal to my MV final, which is 0. So I get 0 at the end. So it looks really similar to, like, this part looks really similar to our free body diagram, because it is a free body diagram. The only difference is that it's multiplied by however much time that free body diagram was working, like creating an impulse on it. So now I have mv0 minus f delta t equals 0. And I have one equation, one unknown. I don't need another, like, kinematic equation or anything. I can plug in I'm solving for the wrong thing. Delta t is mv0 over f. And if you kind of keep track of your own units or your own equations, you'll probably get the same exact equation. But here we just got it in one step. So sometimes it's super helpful to do it this way. Other times, yeah, do what you know, do what you love. So we get 10,000 times 50 all over 100 kilograms, or wait, yeah, it's a kilogram meter per second. This is a kilogram meter per second squared. So we get 2 of those zeros knocked off, and we end up at 500 seconds. 5,000? Wait, which one is it? 5,000, thanks. Kind of cool. And a little bit of magic saves some differential equation solving, because we already have that relationship there. And that is how many hours? Divide by 3,600. Yeah, 1 1/3. 5, 1, 2, 3. Divide by 3, 0, 0. Yeah, 1.4 hours. So 1 hour and 20 minutes. It's a lot of thrusting. Phrasing. We got there. We'll get there. Oh yeah, I guess other thing that's kind of nice. It's like, all right, that tells you how long it took. But you might also want to know, like, well, how far did we travel? It's been 5,000 seconds. Like, we're still moving for another almost hour and a half. Like, how far did we move? Like, what's going on here? And with that, we could do the same thing. Like, 1/2 mv squared plus ft time, well, I guess really minus, right? Minus f delta x is all equal to 0. And now we have one equation, one unknown to get how far did we travel. We're not really asked for this in the problem, but if I want to know delta x equals 1/2 times 10,000 times 50 meter per second squared all over 100 newtons. We went 5,000 times 2,500. Went pretty far. Divide by 100. 5, 1, 2, 3 times 50 times 50 over 100. We went 125,000 meters. It sounds like the diameter of the Earth-ish, something like that. So hopefully the asteroid was not like right in front of us or something. Like we're not trying to avoid something. Hopefully we have space to deal with it. Well, it said deep space, so there's lots of space. Then the fun stuff you can do with all these new methods, right? Now 4/6. This one I gotta make a little smaller so I have some room for it. Yeah.
I guess I kind of have a question, but we go back to 4.2 real quick.
Yeah. It'll catch up.
Yeah, the terms is like the f delta t, the f delta x. Is there like a name for that, like where that's coming from?
Yeah. So this, make it pink. So sometimes what you'll see is like an impulse. So impulse is always the integral of a force through time. So if I have like a known force applied for a given amount of time, like if it's constant, then it's force times that time. But a lot of times what you'll see is like an F bar, that the average force applied over a given time is the impulse. So that's the impulse. And then this F delta X, this one is work, which is F dx. And you can also kind of write that as like an average force over a given delta X. A lot of times people use like the actual integral of force through a distance. Like if you're trying to describe work done by a spring, and you integrate Fkx, and you end up with kx squared over 2. But sometimes there's just like questions where you need to know, like, all right, my car was doing 50 miles an hour, now it's doing 0 miles an hour. My brakes were not always the same pressure. Like I didn't apply the same braking force the whole time, but I do want to know what was the average force to get from 50 to 0. And it's going to be that 1/2 m of the car times that change in v squared. And that would give us like an average force over that distance. Yeah. Nice. Good catch, because that is a good question. So this one is going to be like we're going to be like getting real into it, doing some math, doing some cross products. So before we jump into like mathing our way through a problem, let's just identify like big picture. What's the goal? What are we trying to do here? So there's a lot of systems where angular momentum is conserved. So the first question about that is, what the heck's angular momentum? What's the difference between momentum and angular momentum? Yeah. If it's moving circular, okay. So angular momentum has to do with like, it has to be rotating? Does it have to rotate? Maybe. But there's always some like respect to, right? Like when you talk about angular momentum, momentum, a lot of times we just say like, okay, it's mass times velocity, and the assumption is with reference to some fixed motionless system. So a lot of times the Earth is our reference frame. With angular momentum, there's never a fixed point that is like the point of angular momentum. If you're talking about like solar system, maybe you would choose like the sun, since everything's sort of rotating around the sun, but you always choose a 0 point for, if your radius to this is 0, you have 0 angular momentum, r0. So it's something about like distance and momentum. So if I have momentum mv and I'm farther away from something, I have more angular momentum. And if I'm really close to it, then I have almost no angular momentum. What does that one kind of look like? Distance, momentum. Are there any forces? Is there anything that like causes motion that has to do with distance and force? Oh yeah, that's true. Distance and force is work. Yeah, yeah, distance and force. That one's like dot product. Yeah, yeah, that's true. The units end up being the same too, which is even more confusing. Like work, and then the other thing that I was thinking of, that's like a cause of motion from like for vehicles. Yeah, like torque. Yeah. So work and torque have the same units. So a Newton meter could be 1 Newton applied 1 meter away from where it's acting, or it could be like I pushed this thing with 1 Newton for 1 meter. But so with things that are like rotating, like the way you change angular momentum, like if I apply a torque, angular momentum has to change. But in a case where a spring is like pointing back through the origin, we don't have any torque. Like there's no, or even like gravity. Gravity does not apply torque on anything. It never causes rotation. Whatever rotation you started with, that's just what you have from gravity. So a lot of times this left-hand side, R cross F, the torque, so however much torque we have, or moment, a lot of times it's called moment, that's equal to our change in angular momentum. So if we can identify, in this problem, if we can identify what angular momentum is, and then show that there's no torque applied in that system, then we can say, all right, yes, this is a constant angular momentum problem, and then go from there. Kind of makes sense? That's what we're, at least this is the goal of this problem. It's like a long journey of identifying some things, writing out some equations, and then coming to like, yes, conservation of angular momentum problem. H, yeah. So H is like our variable to say angular momentum. Like P is linear momentum. So it's R cross P is our angular momentum. All right, so we're gonna start off in this frame. So a frame that is moving, this reference frame has a constant velocity. And I wanna know what is the angular momentum of this mass P as it's moving. That's the first thing that we want to know. It's like how do we write out angular momentum? So we need position of P crossed with, and I mean M is a scalar, so really it's like R cross V all times M, like that. And all P slash O prime, so like with respect to that moving reference frame. What do you think? Can you find that cross product? Maybe. see what people are doing. Yeah, you could do it based on find the angle between the two, and then find the sine of them, and multiply the magnitudes. Yeah, well, it's like moving. In this case, it's going to move on elliptical around, where O is like the center of the ellipse. Or the center. I forget if it's the center or one of the sides of the corner. But it's going to look like it works. Yeah, like you could have cosine, sine, cosine thetas, or say that there's a unit vector that points along theta, and you get to those equal elements. Yeah, that would work. And, you know, like R is a function, like position R is a function of time, and as it moves around. Just waiting. So, a lot of times, like, we're just trying to make a definition for the variables, even if we don't know what values they have. Yeah, so like if I say I want to use Cartesian coordinates, its position is x times v1 and y times v2. That's or if I want to say that it's cylindrical, then it's r times er. I don't know what r values are, but I know that once I solve the problem. Similar spot or yeah. Yes. Yeah. Yeah, from O prime, you want E to get out to its position. Things a cross product. This means when you send these things to work, which is R cross it ends up being torque times time. Torque applies, given the amount of time is change medium. No, I don't have the moving around. I mean, it doesn't say that, but it's all if you give it an initial velocity, like spring stretch, throw it. Like one thing that it could do is just move the circle. In general, some major minor. Yeah. I mean, it's a little hard to be yearly. All right, quick survey of the room. So it's pretty stuck as to like what are we even looking for? What is my name anymore? I'm lost. That's okay. To like take a couple of steps back, like all we're trying to do is choose coordinates at this point, and then the math from there is just like it's taking a cross product. So here we have something like if I take this mass and let's say the spring is like not stretched and I try to throw it, then it's going to move around in some kind of like at first it'll try to keep the spring stretched, but it has no outward velocity, so the spring will bring it in. But the closer it gets in, the faster it moves, so then it'll, sorry, I didn't draw the ellipse very well, but it'll go around in some kind of ellipse path. So its radius is changing and its angle is changing. And if we knew the answer of like this is my radius as a function of time and this is my angle as a function of time, we could like plot it out. But right now we don't know that. We're just trying to figure out how do I relate stuff. So if I want to say this is cylindrical coordinates, like there's rotating motion in here, it makes sense to use. At least I think it makes sense. You can also say you're crazy. Cartesian coordinates always make sense. I'm going to use Cartesian, and it'll work out. It'll work. You end up doing a little extra math at the back end rather than the front end. So my position is R of P O prime RER. That's it. There's some radius. There's some unit vector. I don't know how big the radius is. I don't know where the unit vector is pointing. But if I describe where this thing is, I can do it with one radius, one unit vector. Kind of makes sense where I'm going from there. Like a little less stuck at least, because at least we have like something to grab onto. What does velocity look like? There's going to be something along that ER, something along E theta. What are those? Like how fast? Here, I'm going to delete that arrow here. How fast am I moving away from O prime? Like, what do I need to describe radial velocity? Sure. Yeah, how do we want to do this? If we knew like let's say I knew that this was the function. I don't think this one will work, but it's something like this, where radius is changing, like it's coming in and out, and the angle just keeps increasing for all time. It's just spinning around in a circle. It's not increasing at a constant rate, but we don't have to worry about it. So if that's what's happening to this object, how fast is it moving? Like, how do I describe how fast it's moving? You know how to do that? Yeah.
Would it be 1/2 K R sine theta plus R cosine theta in parentheses rate?
What's the K? 1/2 K?
Here, we're on a spring, right?
Yes. Yeah. But we shouldn't need the spring to define the kinematics. Like, so the kinematics should just be like a description of where it is, how fast it's going, and how fast its velocity is changing. Is it r dot theta dot? Yeah, so could we just say that this is like r dot and theta dot, like that? Is that velocity? So then we would always, in that e theta, it's always 5, like at least in this case, it's always 5. Like it's always doing 5 meters per second in a circle. Does that sound right? So at least in, man, terrible. At least in this case, this thing is like traveling around in this path of like a sine wave that is moving around at a constant rate. If I move closer to the center, am I still doing the same speed? Like if I'm rotating at a constant rate, something changes, right? Like there should be some, like the amount that I'm moving, or like, yeah, 2 people. Usually the example is like record players. Oops. We'll say 2 people. Like person 1, person 2. Person 2 is moving faster to the left, right? Bigger speed than that person. Then we also need like that, just the term to say that we've got r and theta dot. So the bigger the radius and the more and the faster theta is changing, the faster I'm moving. Kind of. And as far as like that the first like part A, oh, I guess I asked for angular momentum. I jumped the gun. Like, but I guess that's all we're trying to do, right? I just get excited. So we're trying to define those 2 terms, and you can define it as like x and y if you want, and then it would be, but then we need to figure out like, yeah, how we'll do those cross products. It does work out in the end, just takes a lot of work. So my position is RER, Then I have r dot along that ER and r theta dot and that E theta. And that's my part A. And how are we doing? No time, so I don't want to do anything else. But yeah, I guess I'll leave with that kind of parting wisdom on this stuff is like, if it feels like there's too many unknowns, like the one thing that we just need is just definitions. Like how do we take what we can like think about? Like I know it has a position. How many terms do I need to describe position? And here it's like a unit vector and a magnitude. That's it. That's all we need. Then we can move on from there. Cool. Thanks a lot.